Good afternoon, my name is Cheo. I'm a graduate student of Hanyang University, Korea. My advisor is Professor Simon Song. Today, I'm going to talk about flow visualization on wire-wrapped 37-rod bundle for sodium-cooled fast reactor by magnetic resonance velocimeter. First of all, I will explain the background of our research. SFR is next-generation reactors using liquid sodium as a coolant. And it's very important because SFR can solve the storage problem of spent nuclear fuel by reusing it. In the SFR core, a complex wire-wrapped rod bundle is applied. In order to predict the cooling performance and safety issue, it is important to understand the coolant flow characteristics inside the fuel rod bundle. In order to understand flow characteristics in fuel rod bundle, many computational analyses have been performed, but due to geometric complexity, only 1D or 2D analysis or simple CFD analysis has been mainly used. Experimental data for validations is very scarce. Although Ghost performed flow visualization using 2D PIV, but they still did not obtain the whole velocity field. Recently, using MRV, Pyro obtained a 3D velocity field from just simple circular rod bundle. This study only targeted simple rod bundle but demonstrated the ability of MRV to measure 3D 3C velocity fields in complex and opaque structures. MRV is the best suited for a complex fuel rod bundle. So, what is MRV? MRV is a versatile technique to measure a 3D 3C velocity field using MRI. We can get velocity field from the signals emitted from hydrogen in water. MRV has many strengths compared to existing optical-based flow visualization techniques in various aspects such as non-invasive, no-need particles, adapt for opaque and complex geometry, and it has very short measuring time, etc. So we are gonna use this MRV to visualize the flow inside wire-wrapped rod bundle. So, in this study using MRV, we performed 3D flow visualization on wire-wrapped rod bundle. First of all, securing benchmark data is our first goal. And using the 3D 3C velocity field, we investigate how the wire structure affects the flow distribution and flow structure. Now let's talk about this geometry in detail. A rod is 1.5 meters long and a wire is wrapped on the rod about 7 times with a cycle of 221.5 millimeter. The fluid flows through the narrow passage between the rod bundles in the hexagonal housing, and the wire prevents the rod from physically touching and improves the turbulent mixing performance. Now let's talk about the MRV experimental setup. Based on the starting point of the fuel rod, the position is normalized with the wire lead L. The test section was made using 3D printing. The picture on the left is the schematic diagram of the flow circuit, and the MRV experiment was performed by installing the test section in the MRI bore like this. Working fluid is a copper sulfate aqueous solution at 25 degrees, and the Reynolds number is about 8600. MRV measurements were performed with a spatial resolution of 0.3 mm from 0 to 30.3.7 regions. From now on, I will show you the results of flow visualization. First, these are the measured 3C velocity field from 3.1 to 3.6 region. The contour means the magnitude of the velocity in the streamwise direction, and the vectors indicate the magnitude and direction of the velocity in the direction parallel to the cross-section. The cross-section passes from upstream to downstream. You can see that 4 to 5 vectors exist even in a narrow passage of about 1 millimeter. And as the wire rotates, a vertex is created near the wire it passes through. But depending on the direction of the wire and surrounding space, the surrounding flow pattern changes. Also, if you look at the velocity distribution contour in the main flow direction, you can see that there are high velocity regions and low velocity regions. If look closely, there are a lot of things to analyze, but it is difficult to list them all today. So I want to focus on the effect of wire rotation on the overall flow distribution. Before analyzing the results, we conducted validation, compared the flow distribution within the existing results. By dividing into subchannels like following figure, the flow rate fraction for each subchannel is calculated. For reference data, the flow rate extracted by each subchannel at the Korea Atomic Energy Research Institute and CFD results were used. The x-axis means the subchannel number, and the y-axis means the flow fraction. As you can see, a similar flow rate fraction is obtained for each subchannel group, and it can be said to be sufficiently reliable data. In this slide, I will show you actual velocity distribution along the wire angle and for each position. Although the flow is fully developed after 0.5, the overall flow velocity distribution is non-uniform, and the direction of gradient of distribution changes depending on the wire angle. And then we can find some patterns. Here, black arrows mean wire direction, blue arrows mean the direction of minimum velocity regions in qualitatively. The position of the minimum velocity region could be an important parameter as a vulnerable region to heat transfer. There was a phase difference of about 120 degrees between the wire angle and the direction of the minimum velocity region. The phase difference is maintained, and this follows rotation of the wire. As the wire rotates, phase difference also remains constant and tends to rotate. The following is the results of the transverse velocity field contour and vectors. Contour means velocity magnitude, and vector shows only the direction of the in-plane velocity vector. Due to the wire structure, the transverse direction mixing occurred better. In addition, as the wire rotates, there is a global swelling that rotates significantly outward of the edge region, like this. We can estimate the reason why this global swelling occurs from pressure distribution and flow resistance. The velocity distribution in the actual direction is biased by the wire, and we know that where the flow velocity is high, the pressure is relatively low. Fluids tend to flow from high pressure to low pressure regions. In this cross-section, because the wire is located in the lower left, the flow resistance of the opposite edge region without the wire is relatively lower. Therefore, it can be assumed that such a global swelling motion occurs. Let's summary. In this study, we got 3D3C velocity field of wire-wrapped rod bundle using MRV, and we investigate the effects of wire-wrapped rod on the flow. There is a 120 phase difference between the wire and the actual minimum velocity region. As the wire rotates, phase difference also remains constant and tends to rotate. A global swelling was identified in accordance with the wire rotation. The global swelling is probably caused by the pressure difference and flow resistance due to the presence of wire. Thank you for listening my presentation.